All right. Hello, everyone. Thanks for joining us today. My name is Danica. I'm with 3C Run from the County of San Luis Obispo, and welcome to Intro to Residential HVAC System with instructor Russ Ging from Coded Energy. Next slide, please.
And the button, there it is.
Nice. So before I pass things off to Russ, I just have a few logistical slides to go over. A few quick Zoom reminders before we get started. Please make sure you're on mute for the duration of the training. And we highly encourage questions, and if any questions come up, feel free to put them in the chat, or you can raise your hand and we can unmute you. And this session is being recorded, which will be shared with you along with the slides in the next few days. Next slide, please. And just a little bit about who we are. We are the Tri-County Regional Energy Network, also known as 3C Red. We are a collaborative partnership between San Luis Obispo, Santa Barbara, and Ventura counties. 3C Ren is funded by ratepayer dollars collected through the public goods charge found on our utility bills. And the benefit of being ratepayer funded is that there's no cost to those we serve, and we're able to bring those dollars back into our region. Next slide. 3C Run currently offers 6 programs focused around 3 services: incentives, trainings, and technical assistance. Our training today is part of Building Performance Training Program, and you can find our additional trainings and learn more about our other services by visiting our website, 3c-ren.org. And with that, I'll pass things off to Russ to get the course started. Thank you.
Awesome. Thank you, Danica. Hello, everyone. Thank you for being here. Thank you for taking time out of your day to come and learn this information. It's my pleasure to be here. I always enjoy teaching people about this particular topic. So this class is Introduction to Residential HVAC Systems. My name is Russ King. I'm a licensed mechanical engineer. I have over 35 years experience doing residential HVAC design. And this class is based on a book that I wrote a few years ago, back when I was training lots and lots of HERS raters. And we were getting HERS raters, people coming in to get trained as HERS raters from almost any background you can think of. We had a we had a guitar repairman. We had a guy come in that was a his business was neon lights. He was a neon light artist. We had school teachers, we had bankers, we had everybody coming in, and a lot of those people didn't know anything about HVAC, and we were training them to test HVAC systems. And obviously there was a lot of terminology and stuff like that, and there was no book available at that time that really was really basic. If you Google a basic book on HVAC, it's going to bring up a book on how to install systems, how to charge them, how to check the electrical and stuff like that. And there's very few books out there that really kind of cover the basics. And so I wrote this book quite a while ago, and it has really stood the test of time quite well. And it's a good class for what I like to say, for people who have to work around HVAC equipment without having to work on HVAC equipment. And so HERS raters is a great example. Architects, builders, people in utility programs who need to understand the terminology and things like that. And then also homeowners. A lot of homeowners buy the book when they have to start talking to HVAC contractors, because something that HVAC contractors are quite notorious for is they come in and they will start really laying on thick all the jargon and the terminology and everything, and try to really intimidate homeowners into thinking they don't know what they're talking about, and that the HVAC contractors, should tell them what they should install in their house and stuff like that. And so I like to say, this book helps you fine tune your BS meter a little bit. Um, so it's intended to put you on a more level playing field with the HVAC contractor. And so if they say something, you can look in the book, go, well, that's not exactly what it says here in this book. Um, and hopefully that helps. But yeah, so we're going to talk about how to identify different types of systems, okay? An HVAC, heating, ventilation, air conditioning system. There's a lot of different kinds of systems out there. In California, particularly in the 3C Ren territory, there's not quite as much diversity as there is, around the country. I deal with HVAC contractors all around the country, and there's some pretty interesting stuff out there that even I've never come in contact with, like old oil furnaces and steam radiators and stuff like that. We're not going to talk about that. We're going to talk about the really basic, your typical central ducted system, houses built in the last 50 or 60 years, and things like that, and how to identify them. We'll talk about some of the terminology that's used a lot with HVAC. We'll talk about airflow. Airflow, even really experienced HVAC contractors honestly don't have a clue about how airflow really works. I'm on a lot of Facebook groups for HVAC contractors and installers, and some of the things they say is just like, "Oh my goodness, how long have you been in the business and you still think these sorts of things?" Um, and so, understanding airflow, I think, is pretty simple. It's pretty straightforward. The main thing to know about airflow is 90% of the time, more is better. Okay, anything you can do to increase airflow, and you really want to resist the temptation to reduce airflow in any way by closing off dampers to try to get more air to go somewhere else, things like that. So we'll talk about that. We'll talk about comfort issues, things that cause various comfort issues, and primarily we're talking about differences in temperature. We have a whole class on diagnosing comfort problems in homes, if that's something that you're interested in. We'll talk about some design strategy, and we'll talk about efficiencies and things like that. But first, we're going to dive into some really, really, really basic terminology. Okay. So the first thing is a BTU. What the heck is a BTU? And if we're not careful, somebody's going to try to change the name to American Thermal Unit pretty soon. But for now, it's still the British Thermal Unit. And it's a unit of heat energy. Okay. It's the amount of heat approximately what's stored in a wooden kitchen match. If you just take a wooden match and you strike it and you let it burn all the way down, you drop it, you've just released 1 BTU of heat into the air. Okay. And so we think about BTUs as moving from one place to the another, okay? BTUs coming into our house, or BTUs escaping from our house, or BTUs coming out of a furnace, or BTUs coming out of a heat pump, or BTUs being sucked up by an air conditioner, things like that. And when we talk about movement of BTUs, we talk about it as a rate. So BTUs per hour is what we're talking about. And so just as an example, one of the smallest gas furnaces you can buy is like a 30,000 BTU per hour gas furnace. And so what that means is it's creating 30,000 kitchen matches worth of heat in an hour and putting that into the house. So that's kind of gives you an idea for what we're talking about when we talk about BTU. So it's heat, okay? And you should always think of heating and cooling as a movement of heat. As heat is going from one place to another. Okay. We don't put coldness into a house. We don't put coldness into our refrigerators. We remove heat from them. Okay. We're extracting heat. That's what an air conditioner does. Okay. It extracts heat. So when we heat a house, we're adding BTUs. All right. There's already BTUs in the house, but there's not enough. All right. And so when we talk about think of temperature as the density of heat in a house. And if we add more BTUs to that house, the density goes up. So the temperature goes up. Okay. But in the wintertime, BTUs escape. BTUs are leaving. And so the density drops down. We have to put more BTUs in to bring it back up to the density that we want. Okay. And but when we cool a house, we're removing heat. So there's more heat on the outside and it's trying to get into our house, and it is getting in. It's coming in through the windows and the doors and leaks and everything out else. And so the density of the BTUs gets higher, so the temperature goes up. And so we have to extract those BTUs in order to bring the temperature down. Okay. And the way we extract those BTUs is very interesting. And that's by creating something that's colder than the inside air that absorbs those BTUs and then we take it outside and throw them outside. Okay. And so that's the refrigeration cycle, which we'll talk about in a few minutes. All right. So always think of heating something is adding BTUs and cooling something is removing BTUs. Okay. Now here's a pop quiz question for you. If I put ice into a glass, if I have a glass of water and I add some ice cubes to that glass, did I add BTUs or did I remove BTUs? Now the temperature of the water goes down, doesn't it? And so the question is, did I add BTUs to that water? Well, if you remember that BTUs is the density, or sorry, temperature is the density of BTUs, I added some mass to that water, so the volume gets bigger and the number of BTUs in there is less on a volume on a density basis, so the temperature goes down. But I actually added BTUs. There's BTUs even in a block of ice has BTUs in it. It's just that when I put that ice in the water, I've diluted the BTUs as a total volume. Okay. So adding ice to something, you're actually adding BTUs. All right. There's BTUs in that ice. So when we cool something, we're reducing the density of the BTUs, okay? And by or if we're leaving the volume the same, to change the temperature, we have to remove the BTUs themselves, okay? All right. So the rate at which a home loses or gains heat because of outdoor conditions being different than the inside conditions, okay, we can calculate that. We can say, okay, it's a certain temperature outside. We want it to stay a certain temperature inside. And we've got this house that's separating those two differences. How we can calculate how many BTUs are going to come in and go out. We call that a heating or cooling load, a load calculation. So that's what we mean when we talk about load calculations. Now you may run into other load calculations such as an electrical load calculation, but that's different. So we're talking about BTUs. We're talking about heating and cooling load calculations. All right. So to maintain a constant temperature inside of a house, which is what we want to do, we want our house to stay at a certain temperature when it's really cold outside, regardless of the temperature outside. And we want our house to stay at a certain temperature when it's really hot outside. Okay. And those are actually two different temperatures. It's kind of interesting. In the summertime, 75 is typically good. That's a design temperature. And in the wintertime, 70 is what we like. All right. Um, but we can calculate that. All right. And to maintain that temperature, whatever temperature we want it to be inside the house, in order for that temperature to be constant, we have to be able to add BTUs at least the same rate they're escaping, or to remove BTUs at least the same rate they're coming in. And so that's where the load calculation is important. We can calculate how fast they're coming in, and so we can size an air conditioner that can remove it at least the same rate. Okay. So we want to maintain a constant temperature. All right. And to do that, or the ability to add or remove heat, is what we call the equipment's capacity. The capacity, sometimes referred to as the output. All right. So you've got the load is what the house needs. We can calculate that. The capacity is what the equipment gives us. We can look that up in tables that the manufacturer provides us. And then sizing equipment is the art of balancing what the house needs with what the equipment gives you. Okay. And we'll certainly talk more about that. And if you're interested in the whole design process, we have classes on that too. All right. Okay. So I'm sure you've heard the term tons of air conditioning. This is a 2-ton air conditioner. I got a 3-ton air conditioner in my house. I have a good friend who's an HVAC contractor, and he always likes to tell the story when he calls a homeowner, or the homeowner calls him and says, "Hey, I need a new air conditioner." He says, "Okay, how many tons is it?" And the homeowner sets the phone down and says, "I'll be right back." And the homeowner comes back and goes, "Oh, heck, it can't be more than a couple hundred pounds." So the homeowner actually went outside and lifted up the air conditioner and waited. So the tonnage of an air conditioner has nothing to do with the weight of the air conditioner itself. All right. It's an old term and it goes way back to the days before mechanical refrigeration, when we cooled things with actual blocks of ice. Okay. And we live I should say, I live in a very interesting area in Sacramento, where just up the hill is Donner Lake and Truckee Lake and stuff like that. And they used to they have places up there on the lake that's called Ice House Reservoir, where they would chop up these giant blocks of ice when the lakes froze. They'd chop up these giant blocks of ice and they'd put them on a train and they'd bring them down to Sacramento or even all the way to San Francisco. And that's what they used to cool, vegetables and meat or whatever. And so they would sell ice by the ton. Well, when they came out with mechanical refrigeration, the only way they could explain it to people was to say, "Oh, this piece of equipment will cool the same as 2 tons of ice or 3 tons of ice or 4 tons of ice," or something like that. And so that's where they came up with the term tons, all right? Well, it has evolved to mean, or the true definition of a ton has evolved to mean 12,000 BTUs per hour. Okay, so another way to think of that is a 1 ton of ice can absorb 12,000 BTUs in an hour, and it will melt. Okay, so that's what the term ton means. All right, so 12,000 BTUs, 12,000 kitchen matches per hour is its capacity to extract. All right, so a 1 ton is 12,000, a 2 ton is 24,000, a 3 ton is 36,000 BTUs per hour. So when the manufacturers design an air conditioner, they shoot for one of those increments. Okay, I mean they've designed enough of them that they know how big to make things in order for it to be right about 12,000 or 24,000 BTUs per hour. But then they send it off to have it tested. They send it off to a laboratory, and their equipment gets tested, and then that testing agency sends them back the exact capacity of that air conditioner, and it's never exactly 12,000. It's right around 12,000 BTUs per ton, but they will call it their 2-ton system or their 3-ton system. So when you see tons, that's what we call the nominal capacity. It's a 3-ton. That's just what we're going to name it. We're going to name it a 3-ton system, but the actual capacity may be plus or minus, a little bit, 12,000 BTUs per ton. All right. Now, um, the most standard residential air conditioners typically come in the following sizes: 1.5, 2, 2.5, 3, 3.5, 4. And if for some bizarre reason they skip 4.5 tons and they go right to 5 tons. Okay. So this is very, very common. Most standard air conditioning systems, this is what they're rated at. All right. Now, when this is before mini splits were super popular. Now that mini splits are super popular, they actually go down to half a ton. So you have half a ton, 3/4 ton, and 1 ton mini splits, and then 1.5, 2, 2.5, 3, and so on. And then another very interesting phenomenon nowadays, most heat pumps are variable capacity. And so they have the ability to, like a 3-ton variable capacity will act like a 3-ton, but it can modulate down to close to 2 tons. All right. It can modulate down. And so what the manufacturers have started doing is they're getting rid of the half-ton increments. And it's really bizarre. It's so there's no longer a 1.5 ton. It goes right to 2 ton. There's no 2.5 ton. It goes to 3 ton, and no 3.5 ton four. So there's only even number increments. So 2, 3, 4, 5, 1, 2, 3, 4, 5 ton. And so it's getting kind of weird uh, from what it used to be back in the day. But this is still fairly standard. If you go look at a typical house and you look on the condenser, it's probably going to be one of these. Okay. Um, and so the way you figure out how many tons an air conditioner is if you take the tonnage and you multiply it times the 12,000, you get this number. Okay. And they will typically um, kind of hide a little code in the model number of the air conditioner, and you can figure out what the tonnage is by using this equation. All right, so typically a 2-ton air conditioner will have about 24,000 BTUs. A 3.5 ton air conditioner will have about 42,000 BTUs. Okay, um, but it's not that simple. Air conditioners, the actual capacity that it gives you depends on the conditions that it's operating at. Unlike furnaces, furnaces are dumb beasts. They make flame and they give off heat, okay? Very little will affect the capacity of a furnace. The only real thing that affects the capacity of the furnace is if you go really high up in altitude, because then the air gets thinner, there's less oxygen, and so you have to start derating the capacity of the furnace. But other than that, it just gives off heat and off it goes. Whereas an air conditioner is very susceptible to a lot of different things. The outdoor temperature, the indoor humidity, the airflow, and all this other stuff. Okay. And because air conditioners work by moving BTUs from one place to another, um, their capacity depends on where those BTUs start and where do they end in terms of temperature. Okay. So it's kind of like pumping water up a hill. You can buy a pump that's rated at a certain gallons per minute. And if you're only going to pump 10 feet, you'll get a lot more than what it's rated at. But if you're going to pump it 100 feet up a hill, you're not going to get as much as what it's rated at. And heat pump or air conditioners are kind of the same, and heat pumps too, for that matter. So, the same exact pump, if you're pumping it up a certain distance, you'll get more out of that same pump than if you're trying to pump it up much higher. Okay. And air conditioners are very much the same. So if you've got a what is a 2-ton nominal air conditioner, okay, and you're trying to pump it from 75 degrees inside the house, and you're trying to extract BTUs and dump them outside where it's 110 degrees outside, like in Las Vegas. Okay. We call that the delta T, the difference between the indoor and the outdoor temperature. And this 2-ton nominal air conditioner, which is rated at, 2 tons was 24,000 BTUs, may only give you 22,500, 22.5. So something less than 24,000 BTUs. But if it's only going from 75 degrees up 10 degrees to 85, it might actually give you a little bit more than 24,000. Okay. So you need to know these conditions when you're actually sizing an air conditioner. And you should know those conditions because you'll need those to do your load calculations as well. So the same conditions that we use for our load calculations, we take those same numbers and use them. And you can go to these big, huge, ugly, gigantic tables that the manufacturer provides, and you can actually look up these numbers based on the outdoor temperature or the difference between the indoor and the outdoor temperature, and a few other things like airflow and stuff like that. Okay. So we've got 110. Oh, I forgot there was like animation in here. So 110 outside, 75 inside, we get 22,500. If it's 85 outside and 75 inside, we get a little bit more than 24,000. Okay. Okay. So how do you look at a model number and determine the tonnage? Well, if you take that 12,000 and just think of the 12, okay, look at the number 12. And if you take 1.5 and you multiply that times 12, you get an 18. In other words, 18,000. All right. You take the 2 times 12, you get 24. The 2.5 times 12, you get 30, and so on. So you get these numbers right here. So usually what the manufacturer does is they take this number and they will insert it into the model number of the air conditioner itself. Okay. So let's look at some examples. So here's a condenser. You go out, look at your condenser outside, and you find something called the manufacturer's nameplate. It's going to be this permanent sticker on the side of it. Okay. And if I zoom in on that, oops, if I zoom in on that, here's what I see. And you'll see a model number, you'll see a serial number, you'll see all this Energy Star and UL and all this electrical information and stuff like that. Okay. But look at this model number here, CZH04811B. All right. So if we look at that and we look and we see a 48, somewhere in the middle, we see a 48. That to me means this is a 4-ton air conditioner. All right. The 48 divided by 12 is 4. Okay. And so that's a very good indication that that's a 4-ton air conditioner. Not all manufacturers do it exactly this way. Some of them like to play little games. And sometimes you'll see an 049. Sometimes you'll see the zero in front of it, and sometimes you won't. So there might just be a 48 or there'll be an 048. Okay. Here's another one. This one's a little trickier. So it's a GSX 13030B1 1BA. Okay. So you might see this 13, you go, okay, you see a 30 and then another 30. Well, that's a pretty good indication it's a 2.5 ton. The 30, it's actually the 030 is what it is. If you go look at the Goodman manufacturers books, it'll say GSX is like their brand, their model number. The 13 is the actually the efficiency. This is their 13 SEER air conditioner. and the 030 is the tonnage. So this would be a 2.5 ton air conditioner. Okay. Here's another one. TCGF 36 S4, et cetera, et cetera. Okay. The 36 is a pretty good indication that that's a 3 ton air conditioner. There's no, notice that there's no zero in front of it like there is in the other two, 030, 048. Okay. There's just a 36. Okay. So this just different manufacturers will do it a little bit differently. Okay. All right. Um, Also be aware that air conditioning coils, the coil, we'll talk about what a coil is in a minute, but it's the other half of the air conditioner. The condenser sits outside and the coil is inside. And you know that there's those two copper lines called the line set. They're connecting the condenser outside and the coil inside. Well, the coil inside is can also be rated at tons. All right. And even the air handler, the big box that moves the air, may also be rated in tons. They may say this is a 3 ton air conditioner and a 3 ton coil. All right. And that's all good. But when we talk about the size of a system, an air conditioning system, we always refer to the condenser tonnage, that big outdoor unit. Okay, because for a lot of different reasons, they can mix and match. You can have a 3 ton condenser with a 4 ton coil and a 4 ton air handler, but it's a 3 ton system. Okay. You'll get a little bit more than 3 tons because of the bigger coil and the bigger air handler, but it's still considered a 3 ton system. Okay. Just so you know. Okay. And the condenser, sorry, the coil and the air handler should always be bigger in tonnage than the condenser. You never want to do a 4 ton condenser with a 3 ton coil because then you're pinching off the capacity. You're limiting its ability to be a 4 ton condenser by putting on a smaller coil. But you can always put on a bigger coil to try to squeeze a little bit more capacity out of that condenser. The condenser is like the engine, it's like the heart of the system. Okay. All right. SEER, SEER, and EER, those are the two efficiency ratings for air conditioner. And the S stands for seasonal. EER is energy efficiency ratio. And then they put an S in front of one of them, right? The seasonal energy efficiency ratio. And it's two very similar numbers, but they're tested slightly different. The SEER, the SEER, is tested at varying conditions, hence the name seasonal. So it'll be, milder, warmer, milder temperatures and things like that. And then the EER is like a steady state. They just test it at one temperature and they just see how it goes. All right. Well, SEER, the SEER is a more accurate number to use, but we typically use both numbers when we talk about air conditioning. And then you may have noticed recently they've added a number 2 on the end of those. So now it's SEER 2 and EAR 2. And all that means is that at some point in time they've updated the testing protocols and to differentiate between the old SEER test and the new SEER test, they call it the SEER and the SEER 2. All right. So most new equipment or all new equipment is going to say SEER 2 and EAR 2 on it. All right. So seasonal energy efficiency ratio and then energy efficiency ratio. And these all they send them off to a laboratory and they test them. And this laboratory tests how they test them under certain conditions and they rate them and they put it on their sticker. Okay. All right. Um, let's see. As implied by the extra word seasonal, seasonal just means it's measured over a season. So it's subjected to varying conditions. And then the EER is tested at fixed conditions. Okay. Um, for some strange reason, SEER ratings are always higher than EER ratings for a given piece of equipment. There's no real direct correlation between the two. You can have some pieces of equipment will test very well at the SEER ratings and then not test so well at the EER ratings and vice versa. So, but generally speaking, roughly speaking, the EER is the SEER times 0.875. Okay, but don't assume that that's the case. It's just kind of a give you approximation. Never compare the SEER rating of one piece of equipment to the EER rating of a different piece of equipment. That's apples and oranges. Okay. All right. Both numbers represent efficiency. Okay. So higher is better. Higher is better. So you want higher efficiency. Higher is better. All right. And it's a number that explains what you get out from the air conditioner, which is cooling, which is the ability to remove heat for what you put in, which is electricity. Okay. So you put in electricity and you get cooling out. You get BTUs per hour out. All right. And then that ultimately boils down to watts. How many watts are you putting into this air conditioner per hour in order to get a certain amount of cooling out? Okay, but SEER and EAR, they're unitless. They're unitless numbers. Okay. Um, just like when you go to a car, when you pick out a car, you can pick the engine, you can pick the transmission, you can pick the body type. You can get a 6-cylinder, an 8-cylinder, 4-cylinder. Let's like a Camry. All right, a Camry, you can get a 6-cylinder or 4-cylinder Camry. You can get a 4-door, a 2-door. You can get automatic. You can get manual. Okay, and depending on what you pick for those, you'll get different miles per gallon. And so the same thing happens to air conditioners, depending on your condenser with your coil and your air handler match. You'll get different ratings for SER. And so it's gotten kind of complicated lately. I remember way back in the day, all they cared about was the SEER rating of the condenser with its most common coil match, and they would put a sticker on there, and that's all you had to worry about. But now, because it's getting quite difficult to make houses comply to the energy code, we have to be much more precise on that number. So now you got to go to the AHR website and you got to know the condenser, you got to know the coil, you got to know the air handler model number, you have to know if that has a TXV, you have to know if it has time delay relay and all this other stuff. And then it will give you a very precise efficiency number for that combination of equipment. Okay. Okay. So now let's talk for a second about furnaces. Okay, furnaces are still very common, especially in existing homes. There's a big push now to get rid of furnaces and replace them with heat pumps. Okay, but there's still a lot of furnaces out there, and the efficiency rating that we use for furnaces is it's actually quite simple. It's called the AFUE, or annual fuel utilization efficiency. All right. And it represents how much heat we're getting out based on how much gas we're putting in. Okay. So a unit of gas, of natural gas or even propane, a unit of gas has a fixed amount of BTUs in it. That's the maximum amount of BTUs you can get out of this unit, this gallon of gas or this cubic foot of gas. Okay. It has a fixed amount of heat in it. You put that into a furnace and you get a certain amount of heat out of it. Okay, and it's going to be less than what you're putting in because no furnace is 100% efficient. They're getting close. All right. And you take that heat that's out and you divide it by what's the maximum that you could have gotten out of it. And that's your efficiency. Okay. It's pretty straightforward. All right. So, um, gas has a fixed amount of BTUs in it. If you take the BTUs that you're getting out of the furnace and divide it by how much BTUs are in that gas that you're putting in, that'll give you a percent. All right. And that's the AFUE. So an AFUE of 80 means that you're getting 80 units of heat for every 100 units you're putting in. That's not that good. But that's what furnaces used to be. The older furnaces, not too terribly long ago, gosh, 20, 25 years ago, 80% furnaces were quite common. Okay. And so if you're putting 100 units of gas into the furnace, you're only getting 80 BTUs of heat out of it. And that's not very good. Most furnaces will list right on the nameplate the input in gas and the output in BTUs per hour. Okay. And you can calculate the AFUE. So you take the little number, just remember it's a percentage. All right. It's a fraction. So you take the little number and divide it by the big number, and that will give you the AFUE. So if you got 60,000, you're putting in 75,000. This is right. You got to take the cover off the furnace, and sometimes it's on the inside of the cover. Sometimes it's stuck on a fan or something, or on a piece of metal on the inside. Okay. Here's the model number, the GMP 075. So that's telling you what the input of the furnace is. So you're putting in 75,000 BTUs worth of gas, but you're only getting 60,000 out of it. All right. that's an 80. You take the small number divided by the large number, and you get 80,000 BTUs, or 80%. I'm sorry, 80%. 60 divided by 75 is 0.8. So that's 80%. That's an 80 AFUE furnace. Not very good. All right. That's the older furnaces. That I remember that very first furnaces that these were, even when they were new, they're like 72%. That's terrible. All right. Now think about it though. Where's that heat going? If you're putting in 100,000 on this furnace here, you're putting in 75,000 BTUs worth of heat, and it's burning. Presumably, all the gas is burning. You don't want there to be any unburned gas, but all that gas is burning. But only 60,000 BTUs is actually getting into the house. All right. Where is the rest of that heat going? And these are all the old natural ventilate, or the natural naturally aspirated furnaces, and it was all going up the flue. Those B vents that come off the furnace, those get really hot, and if it's wood's touching them, they can actually catch on fire if you're not careful. Um, and all that heat would go up through the roof and outside the house, and some of it would come inside the house. So they figured out some very clever ways to capture that heat that's going out through the B vent and escaping through the roof by taking the combustion products and running it back through another heat exchanger and let the air cool that down. Excuse me. And so, what happens when you do that is when you burn gas, okay, it gives off these what we call combustion products, all right, including carbon monoxide, but including carbon dioxide, and a lot of water vapor comes from natural gas when you burn it, okay? And so when you take those combustion products, those hot combustion products, and you run that back through another heat exchanger and you blow cool air across it to cool that combustion products, what happens is the water condenses out of it. The water droplets condense out of it, and we call that a condensing furnace. If you've heard the term a condensing furnace, and but now you got to do something with that water, okay? And because it was a combustion product, it's not pure water. It's got some nasty stuff in it. It's not acidic. It's basic, I think, and so you can't just put it anywhere. You have to be a little bit careful out where it goes. All right. But anyways, that's what we call it, a condensing furnace. But the cool thing is they're able to capture a lot of that heat that would otherwise go up through the attic, and the efficiencies go up dramatically. Okay. So here's one. We're putting in 60,000 BTUs of gas, and we're getting out 57. Ooh, that's pretty good. All right. That's um, a much higher efficiency furnace. Okay. And this is probably a condensing furnace. All right. And so 57 divided by 60 is 95. So this is a 95% furnace. That's pretty good. They're getting up into the 96, 97% ranges, are some of the highest ones I've seen. Okay. And so that means they've just figured out how to capture that heat that would otherwise be lost. Okay. So there you go. And you can look at a furnace, you take the smaller number divided by the bigger number, and that gives you the efficiency of the furnace. Okay. All right, now heat pumps. Heat pumps are a little different. Heat pumps are more like an air conditioner, okay? And they're rated in something called the HSPF. HSPF. It's the efficiency rating of something called a heat pump, which we'll talk about later. We'll define a heat pump and explain heat pumps. But it stands for heating seasonal performance factor. Okay, and again, it's how much you getting out for how much you putting in. Okay, and what we're getting out of a heat pump is heat in BTUs per hour. What we're putting into it is electricity. Okay. So we want to get a lot of electricity out of, or want a lot of heat out of it for the amount of electricity that we're putting in. All right. And they test this at certain conditions. All right. And like air conditioners, the HSPF is affected by the condenser and the coil and all this other stuff. So a little preview of what we're going to talk about. A heat pump is basically an air conditioner that runs backwards in the wintertime. All right. So in the summertime, an air conditioner creates something cold to absorb heat and then takes it outside and squeezes that heat out. Well, in the wintertime, a heat pump is the exact same similar equipment, but it's got a little valve in it that switches direction. So now it's capturing heat from outside by making something colder than the outside. It's capturing heat from the outside, bringing that inside and squeezing that heat out inside the house. Okay. We'll talk a lot more about that. but it's electric, okay? And but it's an air conditioner that runs backwards. So the same things that affect an air conditioner and its ability to cool affects a heat pump and its ability to heat. And that's things like how cold is it outside relative to how warm is it inside. And the greater that difference is, the less able that heat pump is to do that. Okay. And then airflow also comes into play as well. All right. Okay. So speaking of airflow, let's talk about airflow. Well, when we talk about airflow, when we quantify airflow, we use a unit called CFM, okay? Cubic feet per minute, CFM. It's used in a lot of different areas in HVAC. Some common places that we use CFM is airflow in a duct, okay? Find your nearest supply register in your house. Mine's in the floor over here. And imagine air coming out of that register, okay? So air is coming out of that register, and if you imagine a cubic foot of air, a box that's 12 inches on a side, a cube, okay, that's 12 inches, and how many of those are coming out of that register in a minute, cubic feet per minute, okay, that's CFM. That's what we're talking about. So airflow in a duct, airflow flowing through a duct, airflow coming out of a register, airflow blowing across a coil, leakage in ducts. All right, when you install a duct system and turn it on, there's little leaks all over the place. And if you add those leaks up, how many cubic feet per minute are leaking out of the duct system? Your house leaks too. On a windy day, air comes in one side of your house and goes out the other side, and we can quantify that in cubic feet per minute as well. Air delivered by a fan. All right, how much air we just like a little desk fan like I have right behind me here. It's about this big around, okay? And it pulls in air and it accelerates this air through a circle about the size of the fan. We can calculate how many cubic feet per minute are passing through that circle. Okay, so we can rate fans in cubic feet per minute as well. So similar to gallons per minute. That's right. You know, when we fill up a bucket of water with a hose and it takes a minute to fill a 5 gallon bucket, that's 5 gallons per minute. Okay, GPM. It's very similar. It's a volumetric. So instead of gallons per minute, it's cubic feet per minute. All right, and it describes how fast a certain volume goes past a certain point, whether it's the face of a register or a point in the ductwork or the opening of a fan and things like that. And if you think about it, it can kind of be fairly easy to visualize. Okay. And so I've come up with this example here. So a cubic feet, I mean, it's hard to imagine cubes coming out of coming out of a register like that. It's easier to imagine circular bubbles. Let's say bubbles. All right. You've blown on a bubbles when you blow like that, and all these little bubbles come out. Okay. Imagine the same sort of thing happening at a register. All right. Well, a cubic foot would be a bubble that's about 15 inches in diameter, about the size of a beach ball, a little bigger than a basketball, about the size of a beach ball. That would be a cubic foot. Okay. So imagine, we'll just call that a big old bubble. All right. This big old bubble of air is coming out. Um, Imagine a nozzle. All right. And one bubble is coming out every second. Every 1 second, a bubble that's 15 inches in diameter forms and then flies off. Okay. 1001 flies away. 1002 flies away. 1003 flies away. So that would be 1 cubic foot per second, which is 60 cubic feet per minute. So that'd be 60 CFM. Not that much air, right? It's not, it would take a little while that bubble would blow up, expand and fly off, expand, fly off, expand, fly off. So you can kind of imagine how much air is coming out of that nozzle when you visualize it that way. So that's 60 cubic feet per minute, 60 CFM. That's a little more than a typical bathroom fan. When you turn on your bathroom exhaust fan, most of those are rated at 50 CFM. So it'd be a little bit more than what they're rated at. Very few of them actually work at 50 CFM because they don't design the ducts very well, but that's a different issue. So 60 CFM. 60 CFM is about how much air you would blow into a large bathroom to heat it and cool it. Okay. um, a typical bedroom in a house, depending on the climate and everything, but the size of the ducts and everything, a typical bedroom you'd blow about 100 CFM, maybe 120, 130 CFM, okay, cubic feet per minute, so 130 bubbles per minute coming out, okay. A typical supply register 90 to 100, so that'd be 1.5 to 2 big old bubbles per second. All right, so 2 bubbles every second. So 1001, 1002, 1001, 1002, all these bubbles. So now it's substantially more, twice as many as 60 CFM to get 120. That's a pretty good amount of air starting to come out of there. All right. Most air conditioners are designed to move 400 CFM per ton. All right. So a 3-ton air conditioner is designed to move 1,200 cubic feet per minute. That's 20 big bubbles per second. 20 per second. Okay. That's how big a 3-ton air conditioner, that's how much air it's intended to move. So that's a lot of bubbles. All right. 5-ton air conditioners, 5 times 400 is 2,000 CFM. Okay. That's what they're designed for. That's what they're supposed to move. Now, the question is, did they size the ducts correctly to allow that many bubbles to pass through the duct system? And that's where things start to fall apart, because they don't. They typically don't. The air handler that's attached to this 5-ton air conditioner needs to and wants to move 2,000 of these bubbles through the duct system. But if you don't size the ducts correctly, there's not enough room. There's too much resistance. The it's trying to trying to push air through a pinched off straw. Okay. And then what happens is the air backs up. And now remember, I said one of the things that affects an air conditioner's ability to cool is how much air is blowing across a coil. So instead of 2,000, you might only be getting 1,700 or 1,600. And now it starts to affect the air conditioner's ability to cool and its efficiency. It's a double whammy. All right, and we'll talk a little bit more about that. So try to estimate the airflow out of a supply register by putting your hand over it, and imagine how many bubbles are coming out per second. Okay, put your hand over a register and feel it, and kind of imagine these 15-inch diameter bubbles forming on this register, and just count how many there are per second. How many you think there are per second, and then multiply that times 60, and you get pretty darn close. There is a tool, however, that allows you to actually measure airflow, and it's called a flow hood. It's a big scoop, all right, and it's got a base on it, and you put it over the register, and you push a button, and it'll tell you. And we used to get very competitive. We go out and measure airflow, and we say, okay, everyone, put your hand over the register and guess what it is, and then we put the flow hood over and measure it, and we got pretty darn close after doing that for quite a while. We could get, within 10% or so of the airflow by putting our hand over it and measuring it. So it's a fairly intuitive thing that you can get pretty good at. Okay, so that was airflow. We're gonna come back to airflow in a little bit. Let's talk now about how homes lose and gain heat. Okay, and I'm going to go a little faster because this is kind of pretty basic stuff, and a lot of you have probably dealt with this before. So when we say convection, that's heat being moved by moving air. Okay, air is moving and it's taking BTUs with it. Okay. And that's convection. So when we talk about how leaky a house is and air is leaking into our house, that's a form of convective heat transfer. Okay. Homes lose and gain a lot of heat by convection. Infiltration, drafts, ceiling fans, stratification, hot air rising. That's the true definition of convection, is that warmer air will rise and cooler air will fall. Okay. The other form of heat is conduction. That is heat passing through a solid object. So if I put coffee in this mug and I feel heat on the outside, that is BTUs that is passing through the ceramic of the mug itself. And in a house, that's heat passing through walls, passing through glass windows, passing through the ceiling and things like that. Okay, that's conduction. All right. And then another form of heat transfer is radiation. Radiation is heat that moves by means of light, essentially electromagnetic radiation, both visible light and light that we can't see. Okay. And if you've ever seen in pictures or if you've ever looked through an infrared camera and you look and it shows, hot things glow orange and cool things are blue, you're seeing that electromagnetic radiation, the infrared light that's coming off of there. And in homes, houses lose some heat through radiation, but it's very, very minor. But in the summertime, houses do gain a lot of heat by radiation, and that's sunlight. Sunlight is a form of radiation. And so when that sunlight comes in and hits the window and passes through the window and comes inside, when that sunlight hits something, it creates heat when it hits something, and that's a form of radiant heat gain. And it's very, very important, obviously, in when we calculate our loads for air conditioning, radiation is a big deal, but heat loss in the wintertime, we don't pay much attention to radiation at all. It's interesting. Okay. Now how houses heat gain and lose heat is through all three of these. All right. Convection, conduction, and radiation. We have to keep track of all those, especially in the summertime, lots of radiation. All right. So the sun shines on the roof, it heats up the roof. That's radiation. This heat then conducts from the roof through the roof surface into the attic. All right. And then it radiates into the attic. Then that hot attic, the air will circulate inside that hot attic. That's a form of convection. And then that heat will get to the insulation and will migrate through the insulation and conduct into the ceiling of the house. Okay. So it takes all three of those for heat to get into a house. All right. And here's just a diagram that shows that. So radiation hitting the roof, conduction is conducting through the roof membrane itself, it's conducting through the ceiling, it's radiating from the underside of the roof deck into the attic. You've heard of radiant barrier. Okay. Radiant barrier is a shiny material that they put on the underside of the roof deck. And the interesting thing about that is a shiny surface doesn't reflect heat as much as it prevents heat from radiating away from it. Okay. And so they put it on the shiny side down, that the roof gets really, really hot, and that shiny surface prevents that heat from radiating into the attic. So that what that heat has to do is it has to go back up and radiate out into the sky. All right. You've seen those survive the cheap little they're not cheap, they're little the little really flimsy little blankets, the little mylar blankets, survival blankets. They're really, really thin, like the mylar of a balloon, super, super thin. But you put that around you and they actually make you feel quite warm because they prevent your body from radiating heat. We lose a lot of heat through radiation. And so when we put that blanket around us, it stops that radiation. Doesn't stop convection or conduction very well, but it stops radiation very well. And it actually helps us stay warm. Okay. Okay. So now, by the way, if you're following along in the book, we got the page numbers up there. So we're on page 15 in the book. Um, let's talk about HVAC systems now. Let's get to actual HVAC. So there's many, many types of HVAC systems. They may or may not have air conditioning in the 3C rent territory on the coast. There's probably quite a few houses that don't have air conditioning. All right. But as we know, and it's like cars. You can't buy a car without air conditioning anymore. So it's kind of hard to buy a house without air conditioning. But some systems have air conditioning, some systems don't. We're just going to kind of assume that they all do. And by the way, if you get a heat pump, you get a free air conditioner when you get a heat pump. Did you know that? Um, so the two basic configurations of HVAC systems are split and package. Okay. Split means that the condenser is in one location and the coil is in a separate location, usually inside, and they're connected by refrigerant lines. Okay. That's a split system. There's another type of configuration called a package unit that's not as common as they used to be. They were very, very popular in the late 70s, 80s, and they're called package units. And that's where the condenser, the coil, and the air handler is all smushed into one box. Okay. And we'll look at some diagrams for that. So a typical split system, okay, has a condenser, and then this is the line set that we talked about, the refrigerant lines. So the condenser and the coil are separate from each other. This is outside and this is inside the house, in the garage or somewhere sheltered from the weather. Okay. So we have the condenser and the coil. And because these are in separate locations, we call that a split system. All right. But it's also going to have some sort of heating unit. In this case, this is a furnace. This is where the gas burns inside these tubes and the air blows across it. And there's going to be an air handler. An air handler is whatever has the box that has the fan in it that blows the air through the ducts. We call that the air handler. All right. So there's four basic parts: the condenser, the coil, the heating unit, and then the air handler. Okay. And by the way, on a heat pump, the coil provides cooling and heating. So this heating unit part goes away. All right, on a heat pump. All right, so that's a split system. Um, Note that we can the air handler, we can describe that as an upflow, a downflow, or a horizontal, and that's based on the direction that the air is blowing. Okay, so you've heard the expression an upflow furnace or a downflow furnace or a horizontal furnace. That just is the direction that the air is blowing. So this example here, this is an upflow air handler, and or you can set it on its side, and it can be a horizontal furnace, or you can flip it upside down and it can be a downflow furnace where the air blows down. Okay, that's what I have in my house. It's a downflow furnace. The air blows down. I live in a raised floor house, so all the ducts are in the crawl space and all my supply registers are in the floor. Okay, so that's a downflow. A package unit, so this is a split system. The condenser's outside, all this other stuff is inside. Okay, a package unit, these are all squashed into one box. And because it has a condenser in it, it has to be outside. So this is a package unit. So it's got a condenser, a coil, a heating unit, and an air handler. And these package units can be either sitting up on the roof of the house. If you drive down the Central Valley, if you drive down 99 in the Central Valley, you look off into those neighborhoods, you'll see millions of package units up on people's roofs. And it's these big greenish gray boxes that sit up on their roof. That's their HVAC system. It's all in one box sitting up on the roof. They can also sit on the ground next to the house if it's a raised floor house, and the ducts can go into the crawl space, or it can sit up on the roof and the ducts all go down into the attic. Okay, so that's a package unit. Not nearly as common as what we used to see back in the day. Okay, but in case someone says, "Oh, that's a package unit," now you know what they're talking about. They're all in one. It's either going to sit up on the roof or it's going to sit on the floor. But the vast majority of systems that you're going to see nowadays are split systems. Okay, there's going to be a condenser outside, and it might look like this, but you'll see some of the newer condensers, like the mini splits, are what we call a suitcase condenser. They're more tall and narrow, and the fan blows horizontally instead of the older style like this one, where the fan blows out the top. Okay, but it's still a condenser and it's still a split system. Okay. Mini splits, a mini split is a split system. Okay. And there's ducted and ductless mini splits. All right. So there's an indoor unit and it can be ducted or ductless. And there's an outdoor unit. And so it's a split system because they're in two separate locations. Okay. You might hear the term DX. That just stands for direct expansion. And that just means that the air is coming in contact with the refrigerant that's expanding. It's actually happening inside a coil, direct expansion. Okay. Package DX, split DX. Don't hear that term too often, but that's what it means. Hydronic heat pumps. Okay. Most heat pumps get their heat from the air, and we'll talk a little bit more about that. Most heat pumps get their heat from the air, but they can also get their heat from the ground or from water. So we might call that a geothermal heat pump or a ground source heat pump and things like that. Okay. Um, Let's see. Another type of package unit that you I'm sure everyone has seen one of these, and it's what you typically see in a hotel room. All right, when you go into a hotel room, next to the window or under the window is going to be this unit in the wall. All right, that's a package unit because it's all one box. The condenser is outside, everything else is on the inside, but it's one unit. It's a package unit, and we call it a package terminal air conditioner or a package terminal system. Okay. Very common in hotel motels. A window air conditioner, just a little tiny window air conditioner that you set in your window. That's a package unit too. We call it a PTAC, package terminal air conditioner. Okay. Here's a PTAC that you would see in a house or something like that. Okay. Or sorry, in a hotel room. So the outside is the condenser, the inside is the evaporator coil side. Okay. So the heat is the air is passing through and getting cold. on this side, and the outside air is coming in and picking up heat. So the heat is being moved from the inside of that to the outside. We'll talk a little bit more about that. All right. Another common, well, not very common. You guys probably don't see too many of these in your area, but in the desert, these are very common. Evaporative coolers, also called swamp coolers. Okay. So it's basically it's a reservoir of water with a little pump, and the pumps it up, and the water trickles down through these mesh pads, and then the air blows through that mesh pad and it evaporates the water. And when water evaporates, it absorbs heat. So when water turns from a liquid to a gas, it absorbs a lot of heat. And so when you absorb heat from the air, it cools the air. So that hot, dry outside air gets cooled and gets pushed into the house. Okay. And we call that a swamp cooler. It doesn't work on really, really hot days, but it can substantially cool the air coming into the house. So you'll see these used a lot in the desert, in the not in the hot summer days, but in the milder summer days, it can actually cool the air. And because the air is so dry in the desert, they work much better. You absolutely do not want an evaporative cooler if you live in Florida or Mississippi, because you're adding moisture to the air that's already way, way, way too humid. And then they won't work very well either, because you if it's not evaporating, if the air is so humid that it's not evaporating the air, it's not being cooled much. So you're just pushing lukewarm, wet air into your house. But in the desert where it's really dry, these work quite well. Gas furnaces. All gas furnaces create B2s by burning gas. Okay. Now, when they burn gas, they give off potentially dangerous combustion products. So there's water, there's carbon dioxide, and there's carbon monoxide. And it's the carbon monoxide that's very, very bad for you. Okay. And all this flame happens inside of a tube, and we call that tube a heat exchanger. You never, ever, ever want the air that's coming into your house to come in contact with those combustion products. You want to keep those separate. So you're burning the gas inside this tube, and all the combustion products go outside the house, but this tube itself gets really, really hot. And so if we can blow air across the outside of that tube, we can heat that air without it coming in contact with the combustion products themselves. Okay, but occasionally on older furnaces, those heat exchangers crack, and now those combustion products are being very, very effectively distributed into your house by going through your duct system. Okay, and that's when things get very, very scary. So you want to make sure that these combustion products never ever get into the house. That's a very, very bad thing. Okay. This is one of the main disadvantages to gas heat over electric heat. And it's my big, big reason why I think people should have heat pumps and not gas furnaces. It's always amazed me. I've spent my entire career designing heating and cooling systems, and it's always made me very, very nervous that builders uh, will pump, will pipe an explosive gas, a very explosive gas. They'll pipe it into our homes where it's burned, and when it's burned, it turns from a explosive gas into a poisonous gas, and we try to get that out of our house. And that doesn't seem to bother anybody. It bothers the heck out of me. Um, but that's just how we typically heat and cool our houses, is by burning gas. All right. Electricity is so, so much safer than gas. And so that's my big reason for wanting to get rid of gas furnaces and go to heat pumps as much as possible. Okay. Um, you'll hear the term central furnace. That just means that the heat is being created in one central location. All right. And when we say a ducted central furnace, that means there's ducts that take that hot air that's being heated and send it to the rooms in different parts of the house. So central means one central furnace. Central ducted just means, there's ducts. Okay. You may have seen old gravity wall furnaces. You go into some older apartments, some older homes. There's this big gray grill on a wall, usually in the middle of the house in the hallway or something. That's a gravity wall furnace. That is burning gas inside there, and the air is just naturally convecting over the surface of that heat exchanger. And then the combustion products go through a flue in the wall, go out through the surface. Okay, but you can actually see the flame. So when you peek inside there, you can see the pilot light, you can see the flame. I remember my grandmother had in the bathrooms of her house, she had a floor furnace in the middle of her house. And in her bathroom, she had these little tiny wall furnaces. They were about, I don't know, maybe 12 by 16 little wall furnaces on the wall. And it looked like a ceramic waffle behind a grate. All right. And you would turn it on and it would light itself and flames would run up this little ceramic waffle and the little ceramic waffle would turn orange and heat the bathroom. I'm a little kid. There's some toilet paper over here. There's flame in the wall. What am I going to do? I'm going to experiment, right? And so I would take little twists of toilet paper and poke it in there. Sure enough, it would catch on fire. This is flame right there in front of your face in the bathrooms. And I just thought that was the craziest thing in the world. And today it still bothers me that we would sleep in that house with gas being burned all over the place. There's classes you can take like through Building Performance Institute, combustion safety classes and stuff like that. When I took my first BPI combustion safety class, I eventually became a proctor. My first thought was, how in the world did we survive all these years by burning gas in our homes? It's crazy how easy it is for things to go wrong. And I'm sorry if I'm beating a dead horse on this point, but if you ever get a permit for anything, anything at all, if you go to the building department and get a permit, if you get a permit to replace your toilet, all right, if you get a permit to replace your toilet in your house, one of the things they're always going to make you do is what? Is put carbon monoxide detectors in your house. All right. Now, I know some pretty large people who eat a lot and and when they go on the toilet, you may want carbon monoxide detectors, but that's not why they put them in your house. They put them in your house because if you have a gas furnace in your house, it is so important that you have a carbon monoxide detector in your house. It has nothing to do with the toilet. All right. If you put a new sink, let me change my example. If you put a new sink in your house, they're going to make you put in a carbon monoxide. If you do some rewiring in your house, they're going to make you put in a carbon monoxide detector. And that is because if you have gas burning in your house, it is so easy for something to go wrong. And very bad things happen. You can Google it and see how many people uh, suffer from bad gas appliances. Okay. All right. Sorry for that diversion. They make fan assisted wall furnaces, same sort of thing. It just has a fan in it. Floor furnaces that my grandmother had in her hallway. She had a grate in the floor. It was always the nice place to stand on a cold winter and let that heat come up under your pajamas and all that stuff. Um, Room furnaces like the little one in the bathroom I was talking about. Um, Now another type of heat that's very common, especially in the 70s when electricity was ridiculously cheap, like 1 cent a 1 cent a kilowatt hour and stuff like that. Um, is electric resistance. Okay. My in-laws lived up in Lake Tahoe, and their house, in every single room, there was this metal box along the side of the wall. And it was about 6 inches by 6 inches long by 6 foot long metal box. And it was electric resistance baseboard heating. Okay. And there was a little knob on it. You turn it and you'd hear it buzz, bzz, and you'd hear it heat up and air would convect through it. And then you start smelling dust burning and stuff like that. All right. That's electric resistance baseboard. Those were very, very common for many, many years. You can have a furnace that instead of burning heat, has electric resistance elements in it. Okay, so electric resistance is a way of creating heat directly from electricity by running it through a wire that has a resistance to it, and that resistance creates heat. Okay, it's a very effective way um, to create heat, but electricity is very expensive. So even though it's a very efficient, it's not the cheapest way to create heat. Okay. And let's see, I think that's all. Okay. All right. Before we dive into heat pumps, let's take a 5 minute break. I've gone a little bit past an hour. So let's take a real quick 5 minute break and we'll reconvene at let's say 4:15. That'll be a 6 minute break. So 4:15, we'll start back up. Okay. All right. So let's talk about heat pumps. I definitely wanted to spend some extra time on heat pumps because they're obviously a big deal these days. So as I mentioned, they're basically an air conditioner that runs in the opposite direction in the winter time. So in the summer In the summertime, they're grabbing heat from inside the house and pushing it outside. In the wintertime, they're grabbing heat from the outside and pushing it into the house. Now that seems weird. In the wintertime, they're grabbing heat from outside. So it's cold outside. Okay. It's 20 degrees outside. It's gathering heat from the 20-degree air somehow and bringing it inside and putting it inside the house. How is that even possible? Well, the way you get heat to move, the way you grab heat is by creating something that's colder than the air. All right. So if the air is 20 degrees, if you can create something that's 10 degrees and you let it sit there, it'll eventually gain heat and become 20 degrees, right? So that air, the BTUs will naturally go inside that object that's colder. All right. So if it's 20 degrees outside, and if we can create something that's 10 degrees, we can capture heat. And then we bring that thing inside the house and squeeze the heat out of it. Okay. That's an interesting concept, to squeeze the heat out of it. But, anyways, that's how a heat pump works. Okay. Now, remember, I mentioned electric resistance heat. Electric resistance heat creates heat by running electricity through a wire of some sort. That wire actually has like ceramic impregnated in the wire, and that gives off heat. Okay. And and that's very efficient. That's like 100% efficient, or darn close to it, like 99.8% efficient, to create heat directly from electricity. But heat pumps, believe it or not, are can be up to 300% efficient. How is that even possible? How can you be more than 100% efficient? Well, heat pumps, they actually cheat a little bit, okay? And so what they do is they move heat. They're taking heat that's already there, and by compressing a gas, they're capturing that heat and bringing it into the house. So instead of creating heat, they're moving heat. And as it turns out, it takes 1/3 the amount of energy to move heat than it does to create heat directly from electricity. So now we can be 300% efficient. And that's why heat pumps are so efficient. We'll talk a little bit more about that. Okay. Another type of heat is hot water heating, also known as hydronic heating. So you have a hot water, you use that hot water to heat air. Okay. You can blow it through a fan and blow air across that hot water inside of a coil like a radiator. That's called hydronic forced air. You can also run it through radiant floors, but you have to have a source of hot water. And if your source is the same water heater that's providing domestic hot water for showers and stuff like that, we call that combined hydronic. Okay, combined hydronic, where the water heater is doing double duty. It's providing hot water for space heating, and it's provide hot water for domestic purposes, domestic hot water for showers and washing dishes and stuff like that. But if your hot water source is only for space heating, we typically call that a boiler. All right. It just serves one purpose. So you have a separate hot water heater for domestic, and you have a boiler for space heating. Okay. The forced air hydronic, as I mentioned, you've got hot water coming in and you blow air across that, and then warm water comes out. We call that forced air hydronic, forced air hydronic. Another type of hydronic is radiant floor panels. You're bringing in hot water, you're running it through the floor under the slab. The slab gets nice and warm, and it radiates heat into the space. So it's a very nice form of heat. Okay. And then that water goes back, it comes in hot and it comes out warm, and it has to be heated back up. Okay. Here's a picture of a radiant floor system in a house that I worked on. And you see they lay these plastic pipes, and then they'll pour another slab on top of it, like a 2-inch slab on top of these pipes. Okay. Um, there are many varieties of residential configurations. All right. And we're going to talk about out west here. And by configuration, I mean, where is the central unit? Where are the ducts? Where are your supply registers? Where are your return grills? Where's all this stuff? There's a lot of different configurations. All right. And whether you choose one or the other depends on the architecture, typically, of the house. Okay. It can depend a little bit on your climate and things like that as well. All right. Obviously, you can't run ducts through a crawl space if it's a slab on grade house. You can't run ducts through an attic if it's a flat roof and there's no attic. Okay, so it just depends on the architecture. Um, generally speaking, a crawl space under the house is a better place to have your ducts in a hot climate because your crawl space stays nice and cool. All right, and your attic can get really hot, so ducts are better in a crawl space typically. But it just depends. It just depends. All right. The other factor is just cost and ease of installation. Um, you know, where you put the ducts there's just a lot of factors come into play. Okay. Um, Before we start talking about the different configurations, we need to talk about, the terminology. So when we say a forced air ducted central system, we mean there's a fan blowing air, okay? It's ducted, so it's blowing air to the rooms, and the heating and cooling system is in a central location. All right. So pretty basic, pretty straightforward. These systems are mostly gas furnaces, but slowly switching over to heat pumps. Okay. They can be with or without air conditioning. Heat pumps have air conditioning automatically. And then the type of ductwork themselves, um, is it can be sheet metal, but most common out here in California is flex duct, vinyl flex duct. Okay. In some parts of the country, they absolutely never use flex duct, and it's very interesting to me that they will only use sheet metal ducts in certain parts of the country. We're out here in California, 99.99999% of all new construction homes use flex duct, and we have been for many, many, many years. And flex duct works great. If it's designed correctly and if it's installed correctly, I would actually prefer flex duct. If I was building my own house from scratch, I would absolutely put flex ducts in my house and not sheet metal ducts. Okay, there's a lot of reasons for that. Okay, so here's just some examples. So in these diagrams, this upper part here, we're looking down on top of the house. Okay. And then this lower thing here is what we call a section. So if you imagine a slice through the house and we're looking at it from the side. All right. So this is a package unit. Remember, we talked about package units. This is a package unit on a roof, and all the ducts are in the attic. All right. So we're looking down on it. Here's the supply registers and the return grill. So everything's in the attic. This is up on the roof. The ducts penetrate through the roof and all the ducts are in the attic. So the return grill with the arrow blowing up and all the supply registers with the arrows blowing down like this. Okay. Everything's in the attic. So very common in the Central Valley. You see a lot of these. Um, Here is what we call an upflow air handler. This is a more typical, this is a split system because the condenser is outside, the air handler is inside. All right, this is a split system. And this is an upflow. So the air is coming in through the return, blowing up, and the air handler is like in a closet or maybe in a garage. Okay. And all the supply registers are up in the attic. Okay. So think about your house. Where are your ducts? In my house, I live in a raised floor. All the ducts are in the crawl space underneath. If I go look at my furnace, it is a downflow furnace. The air is blowing down. All the supply ducts are in the floor. All the supply registers are in the floor. And the return is up above the furnace. The return is high up above the furnace. Okay. Um, this is very, very common in every house built since probably the mid 80s, late 80s. New construction tract homes were all horizontal units in the attic. Most of them. Okay. And so it's a horizontal air handler laying on its side up in the attic. You grow up your attic access. There it is laying on its side. All your supply ducts are in the attic, and the return duct is in the attic as well. Okay. Here's a package unit on the ground, and all the ducts are in the crawl space. Okay. I've seen houses like this where the package unit sits on the ground outside. Everything's all in one box, and all the ducts run through the crawl space. So that's just another type of configuration. Here's what I have in my house. It's a downflow unit. All the ducts are in the crawl space. All the registers are in the floor. Okay. If you have enough space in your crawl space, you can actually put a horizontal unit in your crawl space. So that's what this is. You'll see this more on houses built on a slope where they have, 6 or 8 feet of headroom in a crawl space, and they'll hang a horizontal unit, and all the ducts will be in the crawl space. That's fairly common in some areas. And then if you have a two-story house, you may have to decide. Um, if it's a big enough house, or if you can afford to have two systems, one serving upstairs and one serving downstairs, you can mix and match everything we've talked about up to this point. Okay. The upstairs is probably going to be a horizontal unit serving the upstairs, and then the downstairs, it depends on how much room you've got. If you have a crawl space, you can do ducts in the crawl space like that. Okay. That's fairly common. If you don't have a crawl space, if you have a slab on grade house, you can have an upflow on the first floor and a horizontal on the second floor. That's fairly common. Now, the hard part is getting these ducts through the floor joists. And how is this happening? Okay. That can be a real challenge. And that's typically why ducts get undersized, is because there's just not enough room to fit them. And the architect and the structural engineer didn't coordinate with the HVAC designer, and where the HVAC designer said, "Yeah, man, I need 10-inch ducts going this way. I need 8-inch ducts going over there. I need 9-inch ducts going this way." And they get out there and like, "Oh, heck, only 7-inch ducts are going to fit." And then they end up putting in 7-inch ducts, and that's not a good thing. Okay. Very, very common. If you have a two-story house with only one system in it, the way they typically do it, at least for tract homes, production homes, is they'll put a horizontal unit in the attic, and the upstairs will be served by ceiling registers. And then the downstairs, they have to get ducts from the attic all the way down to the first floor. And they'll do it through these cavities called chases. That's a chase. Okay. CHASE. And they'll just run the ducts down through there, and then the ducts will get to the first floor. But now, how do they get from that point over to the rooms that they need to get to? And that is, I ran two mechanical engineering departments, and that was probably 80% of my headaches came from trying to get the ducts from the bottom of this chase over to the room where we wanted that supply register to be. And it's just because the architects and structural engineers just don't think about that stuff. I had one builder in Las Vegas who's who these floor joists between the floors were 22-inch tall open web floor joists. So you could pretty much run the ducts wherever you wanted to. That was beautiful. But that was only one builder out of dozens that we worked with that did that. Everyone else uses TJIs, which is like a wooden I-beam, and it's very, very diff. You have to get permission from the structural engineer to go across those. So you're pretty much limited to going parallel between the floor joists and getting to where you need to put a supply register. And it can be very, very challenging. Sometimes you have to drop ceilings in hallways and closets to go underneath the floor joists. Sometimes there's beams in the way, and it's a real nightmare. All right. It's a real challenge. Hopefully architects are getting better. Okay. All right. Mini splits. So mini splits is a common term. You're going to hear a lot of these. They've been around forever in Asia. They've been in Japan for 30, 40 years. We've only recently have they started coming into the United States in the last 10 years. They become very, very popular. Okay. And it's important to realize when someone says a mini split, most people think of a ductless mini split. Ductless. So that's just a head on the wall and air comes out of it. Okay. And they heat and cool the room that they're in very, very well. Now, the question is that heating and cooling going to get to the adjacent rooms? And so they say, well, let's put a head over here. Let's put a head over there. And you can do that. But they also make ducted mini splits. So it's a small split system, half a ton, 3/4 ton, 1 ton split systems. Okay. And they will send refrigerant to a small fan coil unit that can mount in a drop ceiling. Sometimes we call those pancake units because they fit in a very small area. And then they can run ducts out to different rooms. Okay. So ductless and ducted mini splits. They're a true split system because the air handler's inside and the condenser's outside. All right. And the ductless versions, we sometimes call that a head or a cassette. Some of them will mount on a wall and some of them will mount in a ceiling, but it's just one. And the hot and cold air come out of that unit. And like I said, they heat and cool the room that they're in very well. Okay. So here's a wall cassette. So I think the warm air comes in the top and cold air blows out the bottom. And this little opening can go up and down, and it's motorized and can move the air around and stuff like that. So that's your heating and cooling is coming out of this unit. There are no ducts. This is a ductless unit. This is one of those suitcase condensers I was talking about. Okay, it looks a little different than the big ones that we're used to seeing, but they are now making these in up to 5 tons that look like this, the suitcase style. Okay, soffit mounted fan coils are the pancake units. Let me show you a diagram. So they only need about 11 or 12 inches of a drop ceiling, okay, and it mounts up in there, and then the ducts can go through that drop ceiling and get to where they need to go. Sometimes the return is right in the face in the bottom. So there's a return grill in the bottom of the unit. You take a couple screws out, you take the return grill, and you're looking right up inside the fan coil unit itself. Very common in apartments, very common in larger hotel rooms. We'll have these in them. Okay. So soffit mounted fan coils, ducted mini splits. There's another type of system called high velocity systems or small duct high velocity. Okay. And what they're basically doing is they got little small duct because of the challenge of running ducts through a house. Someone said, you know what? Let's just use small ducts and we'll just use a really, really strong fan and we'll force the air through these little tiny ducts. And they actually invented this for historic buildings when they wanted to add air conditioning to these historic buildings without having to modify the building too much. And so they said, well, let's just have these little 2 inch and 3 inch diameter ducts, but we're going to use a really strong fan and we're going to cram air through these ducts and the air is going to move really, really fast. So they call it high velocity small duct systems. They work pretty well, but they require a lot of fan energy to do that. Okay. Um, okay, let's talk about some bits and pieces of HVAC systems. Okay. This is a typical horizontal unit. This could be an upflow unit or a downflow unit, but this is a typical horizontal air handler, furnace, air handler, whatever. And it's ducted with flex duct. Okay. So you see how the duct is curvy, it's flexible. And these are very common terms. So we've got a TY, all right, is a way of splitting ducts. We've got ducts, some ducts are branches. So a branch duct is a duct that goes to a supply register. Okay. It's the last run to the supply register. But some ducts will come out and then they'll have to split. All right. And we call that a trunk. Any duct that splits into more than one duct is called a trunk. And you can have supply trunks and return trunks. Okay. And so this duct comes out here and it splits. And so that's a trunk. And this goes to the register. So that's a branch and that's a branch, just like a tree, right? We have something called start collars. That's where the duct connects to this box. Okay, I'll show you a picture of that. Supply registers. Okay, so all these bits and pieces, the air handler, the refrigerant lines, the condenser. Okay, let's look at these in a little bit more detail. So flex duct is very interesting. And it starts off as a metal wire, okay, like a slinky. Like if you took a slinky and stretched it out a little bit, and then you wrap that with plastic, and then you wrap that with insulation, and then you wrapped it again with more plastic, okay? That's basically what a flex duct is. So it has this inner liner, okay? Then it has this wire that's what gives it its shape. Then it has insulation to keep heat from conducting out of it. And then this outer wrapper is just like basically like a plastic bag. And we call that a vapor barrier. Not such a big deal in our climate. We live in a pretty dry climate, but like in Florida where it's super humid, if you don't have a vapor barrier on the outside, what happens is this moist attic air will migrate through the insulation, and when it comes in contact with that cold duct on the inside, moisture condenses and it runs down to the bottom. It'll drip out the bottom and put stains in your ceiling. All right. Or worse, cause your ceiling to collapse. But so they put this plastic bag around the outside of it to keep that moist air from coming inside. We call it a vapor barrier. But in our climate, all it really does, the only purpose it serves is to hold the insulation in place. Okay. But flex duct, very common. Metal duct, okay, straight metal duct. It comes shipped kind of flat, like a U shape, and so they can stack it. All right, they can stack a whole bunch of U-shaped ducts together. But if ducts are round, they can't stack as many of them in a truck. Okay, so they come opened flat like this, and there's a little seam. They bend it over, and there's a little seam that it locks together, and it makes the circular tube. Okay, and so this metal seam, it can leak. It can leak a lot if they don't do a good job sealing it, and so they need to come by and put a bead of mastic on it of sealant. And they you might hear this called KD pipe, and that stands for knockdown. And all that means is they manufacture it and they flatten it out and they knock it down to a flat so that it'll stack. Okay, fairly common. Uh, in some commercial buildings, you'll see another kind called spiral flex, and it's a metal duct that's made out of a spiral of metal. Same basic concept. That seam where the metal connects with each other, if it's not sealed real well, air will escape. Air will leak through there. Even if it's pinched really tight, some air will escape. Air handler. So the air handler is the box, the big box that has the fan in it, the big fan that, and the purpose of that fan is to push air through the ducts. Whatever that box is, we call that the air handler. Okay. It can be a furnace. A furnace is an air handler. Okay. For heat pumps, we don't burn the gas. And so there's a fan and then the coils in the same box. And we call that a fan coil unit. Okay. Fan coils look just like a furnace, but there's no gas. There's no gas being burned. So there's no vents, there's no flue vents, there's none of that stuff. Okay. And the coil, because you always need a coil, is in the same box. And so it's a fan and a coil, and we call it a fan coil unit. Very, very clever naming, right? Um, the air handler is whatever this box is that's got the big fan in it that's pushing the air through the ducts. Okay. You've got supply air ducts. That's where the heated and cooled air is coming out. All right. They're under positive pressure when the fan is on, the air is blowing out of them. Those are supply air ducts. Then you've got branches and trunks. I mentioned that already. Okay. Supply branches, supply trunk. And you can have a trunk, you can have a long, long duct. But a lot of times what they do in houses that have basements is the furnace will be in the basement, an upflow furnace, and there'll be a long rectangular trunk that runs the length of the house. Okay. And then they'll have branches coming off of that to go into each room. Same thing. Trunk splits, branches terminate. Okay. Trunks and branches. And then return air ducts. Return air is the air from the house being returned to be heated or cooled. So it comes out of supply, it warms or cools the room, circulates through the house, makes its way back to the return grill, gets sucked up into the return grill, and returns back to be heated or cooled. So we call those return air ducts. Some people call them cold air returns, but that would only be in a heating climate like up north where they don't have air conditioning. They'll call it a cold air return because they don't have air conditioning. They just have heating. So it's the cold air from the house going back to be reheated. But the more accurate term is just call them return air ducts or return ducts. Okay. And so here's an example of return duct. Here's another return duct. This drawing doesn't have a return trunk. It just has return branches. A return trunk would be where two returns come together and join into one bigger duct. Then that bigger duct would go back to the air handler, and that would be a return trunk. Okay. The way we split flex duct is with a sheet metal fitting called a TY, a TY. And it's basically this conical piece of sheet metal with another little cone coming off the side. And we attach the flex duct here. We attach a smaller one here and a smaller one there. And it's just a way to make one big duct split into smaller ducts. So we call it a TY. Another fairly common way to do that is instead of this sheet metal fitting like this, they'll have these ductboard wedges. We call them cheese wedges, like a a Green Bay Packer cheese hat. Okay. Um, the problem with these is the air gets very turbulent inside. So there's a lot of resistance to airflow. But the reason some contractors like these is because they're basically made on site. Whereas these, you have to order these and you have to bring out the right sizes. So you might have like a 1097 TY, and you've got to buy the right one and you have to have the right one on hand in order to install those ducts. But these, you bring out these cheese boxes and you cut whatever size holes you need and you put a start collar in there to run the ducts out. Okay. You'll hear the term register boots, a register boot. Okay. That's the sheet metal box that's attached either to the sheetrock for ceiling registers or to the floor for floor registers. That's where the duct is connected to the conditioned space where the register will fit inside of it. So it's the transition from the duct to the register is a little box, and we call that a return or supply boot. All right. I mentioned chases. Chases are those vertical cavities in the wall, usually a corner of a closet or a dead space in a corner somewhere where we run ducts to get from the attic down to the first floor, or in some cases the other direction. But it's a boxed out portion of the house that we can run a duct inside. We call that a chase. You've heard me mention start collars. A start collar is a way to connect a round duct to a sheet metal box. Okay. So you got this box, you cut a hole in this box, and you take this collar and it fits inside, and you bend the tabs back on the inside, and it just leaves a little collar around an opening in this sheet metal box. And then the flex duct slips over that collar and they put a big zip tie around it, and that holds it in place. And then they put tape and mastic and all this other stuff to hold it in place. Okay. So that's what a start collar is. It just connects a round duct to a flat sheet metal box. Um, Squared around transition is just a way to go from a round duct to a square duct, whether you're going down in a wall can or something like that. There's a lot of different kinds of fittings you'll see, sheet metal fittings. A wall can is a rectangular sheet metal duct that's small enough to fit in between the studs of your walls. Okay. Not a great idea. I would only use those in very desperate measures because they're uninsulated. And so they'll conduct a lot of heat with the sheetrock and stuff, anything it's in contact with. Plus, there's a lot of resistance to the airflow. The air doesn't flow through these very well. Okay. Um, let's see. Condenser, we talked about that. That's the big thing outside. That it can be this style. This is the older, more typical style, or you can have the suitcase style of condenser, like I showed you with the mini splits. Okay. And here's the coil. I talked about the coil. The coil is inside the house next to the air handler, and it's what the air blows through that cools the air. Okay. And so the way it cools the air, and we'll talk a little bit about this in a minute, is the refrigerant that gets compressed to a liquid. When they allow it to expand into a gas, it gets cold. All right. If you've ever used a Coleman stove or a Coleman lantern, or if you've ever used one of those spray cans to spray air to get the dust out of your keyboard, and you notice that it gets cold, the can gets cold because there's a liquid turning into a gas. It's the same principle. So this compressed liquid expands into a gas and gets really, really cold. And that happens inside this thing. If you look on the side of this kind of looks like a radiator in the front of your car. It's got a bunch of aluminum fins in it. Okay. And these tubes have the really cold gas running through this radiator, and the air blows through there and it cools the air. Okay. And so we call that the coil. So the liquid gas comes in here in this small tube. It goes through this little orifice. It starts to expand into a gas and it gets really, really cold. And then all this gas is collected in this big tube and sent out to the condenser where the heat is squeezed out of it. Okay. And we'll talk about that in a second. That's the compressor is what squeezes the gas. But anyways, this is the coil. There's a lot of different kinds of coils. This is called an A coil because of the shape. So this is an A coil. So you got A coils. You can have U coils. You can have W coils if you only have a certain limited space to work. You can have that's a wider, flatter coil, or even something called a slab coil that's just flat like this. A lot of different kinds of coils. Okay. There's a little thing called a TXV. I won't get into the TXV. It's pretty technical, but what a TXV is, it allows the flow of refrigerant to adjust based on temperature changes. So as the temperature changes, it causes this little needle valve to open and close, and that changes the flow of refrigerant to kind of optimize it. That's how we squeeze a lot of extra efficiency out of air conditioners is with these TXVs. Okay. There's what it looks like, a little TXV. Okay. This is the sensing bulb for a TXV. This is very important to raters. They have to be able to check this. Now, if you go look at your condenser outside, okay, if you have a split system and you got a big condenser sitting out in your yard, there's going to be four things going from the condenser into your house. There's going to be a large gauge wire, electrical wire. That's what provides power to run the condenser. There's going to be a smaller gauge wire. Those are controls, so low voltage controls that comes from your thermostat. All right. There's going to be a large copper tube about the size of your thumb. Okay. And then a small copper tube about the size of your pinky. All right. And those are going to connect the condenser to your house, and they're going to go and do their things inside the house. Okay. Those two copper tubes are called the refrigerant lines. All right. There's a big one and a small one. Okay. The big one has gas in it, and the small one has liquid in it. All right. And we'll explain what that means in a minute. Okay. The term plenum, you might hear me mention a plenum. You got a supplied plenum and a return plenum. Basically, a plenum is a box on the end of an air handler that allows you to attach ducts to it. Okay. So a plenum is just a box that ducts attached to. Think of it that way. Um, let's see. I mentioned supply registers already. That's where the air comes out. Okay. Let me get past this. So when we talk about registers and where we put them, there's a couple things that are important to understand. Okay. There's two kinds of airflow. There's the primary airflow, and that's the air coming out of the register. And then there's a secondary airflow, is like, where does that air go after that? Once the air shoots out of the register and it runs out of velocity, then what is it going to do? Well, it depends on temperatures. It depends on if the system keeps running, there's more air coming in behind it, kind of pushing it out of the way. Okay. But the primary airflow is the air coming out of the register. And the secondary airflow is where does it go after that? Okay. And I have a pop quiz in my classes. I say, what's better for heating? What's better for heating a house? Floor registers or ceiling registers? And 90% of the people will say floor registers. Floor registers are better to heat a house because hot air rises and air's coming out, right? That's what you want. That's not what you want. Okay. It's actually the opposite, because the primary airflow is to blow up and hit the ceiling. And then the secondary airflow for hot air is to stay at the ceiling. That's not what you want. You want mixing. The most important thing that a supply register can do is mix the air. And it mixes the air by having good airflow and being pointed in the right direction. And when I design systems, my general rule of thumb, and when I teach classes, is to blow the air the opposite direction that it wants to go. So if hot air wants to rise, blow it down. If cold air wants to fall, blow it up. If air wants to leave a room, blow it into the room. And that promotes mixing. If air is crashing into itself while it's trying to leave the room, you get better mixing that way. Okay. So there's just some diagrams for that. Unfortunately, you can't have ducts for heating in the ceiling and ducts for cooling in the floor. You got to pick one or the other and hope for the best. Okay. All right. So blow the air the opposite direction that it wants to go. That's one of the most important things I can teach when I teach HVAC design. where to put a register in a house and things like that. Okay. By the way, I know I'm not gonna be able to finish my slides. I almost never do in this class. You guys will get a copy of your slides, these slides, so you'll be able to finish up. So I just want to hit a couple more important things, and that is when we talk about registers, there's two basic types of registers. Okay, there's stamp faced and there's bar type. Bar type are more rare. Stamp face are very common. This is a stamp face and this is a stamp face. A stamp face register starts off as a flat piece of sheet metal and it gets stamped. A big machine stamps it like that and it cuts the blades and presses them out. Okay, it's one piece of metal. A bar type has a frame and then the fins are individual pieces that get inserted. Okay, and the important thing to understand about this is these have much better airflow. I have a, by the way, I forgot to mention I have a blog. It's russellking.me, russellking.me, and I have an article about how you can use these if you have airflow problems in your house. That replacing all your registers with bar type registers can make a big difference. Okay, so that's very important. Let's see. I'm going to skip past the basic thermodynamic stuff. That's really boring. And I want to get right to the concept in my last 2 minutes or last minute is the refrigerant cycle. The way the refrigerant cycle works is, remember I said by creating something that's colder than the outside air, we can absorb heat. Okay. And the way we create something that's colder is by expanding it. So if we have a gas and we can expand that gas and make it colder than the air, it'll absorb heat. And then we take it outside and we can squeeze that heat out of it. So here we have a container of this gas. And when we expand that container, it becomes 40 degrees. Well, the inside of the house is 70. And if it's 40 in this tank and 70 here, heat is going to go inside this tank. All right. And then we take it outside and we squeeze it. And when we squeeze it, it gets hot. It gets hotter than the outside air. So heat will come out. So here it's 40 degrees and it's absorbing heat because it's cooler than the inside. And here it's 100 degrees and it's expelling heat because it's hotter than the outside air. And we can do that by expanding and contracting this gas. So that concept is how the refrigerant cycle works. So think of it as a heat sponge, okay? So the heat absorbs the refrigerator absorbs the heat inside the house and then it's squeezed outside the house. And guess what? You can go the opposite direction. You can absorb heat outside and bring it inside and squeeze the heat out. Okay. So I will leave you with that. And I will skip these last few slides. Oop, too far. And hand it back to Danica and she can close this out.
Yeah, thank you so much, Russ. So as we wrap up, I will be launching our survey, which will let us know your thoughts and what other improvements and courses we should offer in the future. And yeah, please make sure to click submit. So I just launched it. So this is the first time we're launching this survey, so I'm hoping there are no issues on your end. So yeah, thank you. And if you have any energy code or CalGreen questions, Code Coach. We have a Code Coach program to answer those questions for you. Next slide, please. And if you have any questions in receiving your AIA or ICC units, please reach out to my email. And in the next couple of days, you will be receiving an email with the slide deck and a link to the recording. And I'd also like to invite everyone to our upcoming courses. Next week, we have an in-person green building construction tour in Santa Barbara. Also next week, if you just can't get enough of Russ, we have another course. It's Understanding Hearst Registries for Building Departments, which will be a webinar. And if you want to supplement your HVAC knowledge, we have Optimizing Heat Pump Zoning for maximum comfort and efficiency, as well as Mechanical Systems in Detail. And you can sign up for these trainings and see more offered on our website at 3c-ren.org. And with that, I'll pass it back to Russ for any last-minute lingering questions. And if you haven't filled out the survey, please do so.
don't see anything in the chat, but yeah, check out my blog. I have a lot of I cover a lot of stuff in there where I tend to vent. Did
um,
Cole, looks like Cole might have a question, or no, they're unmuted. No, okay.
Thank you guys. It was really educational.
Good. Thank you, Cole.
Have a good day.
thank
You
you.
too.
And I'll leave the course until 5 p.m. Open, so feel free to ask any questions and just hoping to get more survey responses until 5 p.m. So thank you. And also thank you so much, Russ. That was such a good course. I love the terminology portion as well. It's like, okay, let's break it down, but like in simple words.
Yep. Yep. HVAC contractors tend to come in and just start throwing all these terms at you, and you're like, oh my God, I have no idea what you're talking about.
Yeah.
I have to believe you.
Yeah.
Yep.
I liked your joke about how many tons is your HVAC?
Yes. Yeah. Yep. Or they told the homeowner they need a 4-ton air conditioner and they have a rooftop package unit. Like, there's no way that'll hold my roof will hold 4 tons. You're crazy.
That's hilarious.
Yep.
All right. I think that might be everyone. I'll go ahead and end the course. Thank you so much.
Thank you. Bye bye, everyone.
Bye bye.